The topic of this video is electron donating and electron withdrawing groups and what their effects on the aromatic ring are. So as we saw in the previous section of the textbook, electron donating and electron withdrawing groups primarily exert their effect by changing the rates of electrophilic aromatic substitution and also directing groups to different places. So when we're looking at two or more rings or one ring with multiple groups, the important question is to know what makes an electron donating group better or worse. So first of all, what makes one of these an electron donating group at all? This is the most common generic structure for a compound with an electron donating group. So we have an aromatic ring, and next to it is some sort of atom X, and most of the electron donating groups that we'll see have an available lone pair on that atom. Of course, the exceptions to this are alkyl groups, which are electron donating by induction, and halogens, which are actually deactivating groups. So if we want to rank which donors are better or worse, we can use the ARIO rules back from the very beginning of organic chemistry. So for example, if I have this compound here, I have two potential donors, the amine nitrogen and the phenol OH group. So amines versus alcohols. Which one of these is going to be a stronger donor? So take a moment here, try to rank these, pause the video, come back when you're done. All right, so if you talked about these being better due to atom identity, you are absolutely correct. The question we're trying to answer here is which of these two different atoms are a better donor? Is it the amine nitrogen or the alcohol oxygen? Well, if we look at atom identity, those two atoms are related mostly by electronegativity, so the amine would be a better donor compared to the alcohol. It's a less electronegative atom. Let's take a look at an example where atom identity is not the case because we have the same atoms in both cases. Here, we have an amine nitrogen versus an amide nitrogen. Both of these are electron donating groups, but which one is stronger? Think about which effect we're looking at here. Take some notes about which one is a stronger donor, and then come back to the video when you're done. So here, what we're actually seeing is a resonance effect. Both of these are the same atom, but the amine is going to be a much better donor than the amide. The reason why is the amide nitrogen is less available to the ring because it's also participating in resonance with the carbonyl group alongside. So since that lone pair is involved in resonance outside the ring, it's not going to be quite as strong as a donor. Finally, let's take a look at these two. So what I want you to do here is figure out which of these two is a better donor, methyl versus the trichloromethane group, and I'm going to give you a hint here in that this is an inductive effect. So go ahead, pause the video, take some notes. Okay, so this one is probably the most straightforward of the effect. If we pack on all of those chlorines onto the carbon, those will create a very, very strong inductively withdrawing group. So a carbon with 3 halogens on it, unlike the alkyl group, is actually a deactivating group. Well, how about the electron withdrawing groups? Structurally, they have a pattern like this, where we have some atom X that is bound to some other atom Y, and those two atoms have to have differing electronegativities. So the main characteristic for the electron withdrawing group is the polarized pi bond between our atom X and our atom Y. So some examples: the whole carbonyl family, esters, ketones, aldehydes, etc. The triple bond of nitriles, and the NO of the nitro group. So we'll see other examples other than this. For instance, sulfonic acids are also electron withdrawing. They all have this basic pattern. So providing an order to electron withdrawing groups is less important than those for electron donating groups, but there are some general trends. So what we want to do with these groups is we want to sort of put them into buckets. One set will be weakly deactivating, another set will be moderately deactivating, and a third set will be strongly deactivating. In the weakly deactivating group, we have things like the halogens. So halogens deactivate by induction. That's a fairly weak effect. If we start putting polarized pi bonds adjacent to the ring, that's going to be a little bit more deactivating. So both the carbonyl group and the sulfonic acid are moderately deactivating. These are good pi acceptors, so they can pull electrons out of the ring by resonance. And finally, we have the strongly deactivating groups like the nitriles, the nitro group, CF3, and NH3+. So all of these groups have something in common. They're either very strong pi acceptors, so we can draw very good resonance forms for them. They also have highly electronegative atoms, and in some cases more than one, and they have a large amount of partial positive charge density on one or more atoms. In the case of the ammonium ion, we actually have a full formal positive charge on the nitrogen, which contributes to it being a very strongly deactivating group. So let's sort of summarize this. This is a version of the chart that can be found in your textbook. We're going to sort this into activating groups, which are also orthoparadirectors, and deactivating groups, which are also metadirectors. In the middle, we're going to have the groups which are exceptions. So over here all the way on the left, we have the very strongly activating groups, the phenoxide, the phenol, and the amine nitrogen. Now there's an important rule that we have to know here, which is that we cannot actually do electrophilic aromatic substitution reactions on anilines. The main reaction where this is a problem is nitration. Concentrated sulfuric and concentrated nitric acid will actually oxidize this ring and create a whole bunch of charcoal. So it is actually too activated for these types of reactions. So it's important to know that for anilines, these can be primary, secondary, or tertiary amines. Any of those hydrogens can be replaced with alkyl groups, and the effect is the same. Next, we have groups which are activating and orthoparadirecting, but slightly weaker. Here we have the ethers, the esters, and the amides. Ethers are weaker donors than alcohols because they're less acidic, so we have more of a positive charge on that oxygen. The ester and the amide are both less activating by resonance. Finally, the last of the activating orthoparadirecting groups we have are alkyl groups. These are the weakest because they just help by induction. All right, so now we're getting into the deactivating groups. Halogens are weakly deactivating, but they're still orthoparadirecting due to the lone pairs on the halogen atoms. Next, if we have some electronegative bonds, like the sulfonic acid, like the nitrile, like the carbonyl group, these are moderately deactivating, and they are also metadirecting. Then, finally, we have the strongly deactivating groups, like the nitro group, the ammonium ion, and the trihalomethane groups. These compounds are very, very inductively withdrawing or have very strong pi acceptors, and they're going to be metadirectors and the most strong of all the deactivators. Again, here we can have any of those hydrogens replaced with R groups. As long as we have the positive charge on the nitrogen, that means that we're going to have our strongly deactivating group. Here, those can be any halogen. They can be fluorines, they can be chlorines, they can be bromines. The cumulative effect of those is to make them strongly deactivating and also metadirecting.